Yes. So today, we are going to focus on from today now. We are going to focus on learning element of this subject. In particular, we're going to focus on for the first week. We're going to focus on reinforcement learning, and next week, once we have this basic knowledge about reinforcement learning, particularly Q-learning value-based approaches, and then we can looking back to the again to this multi-agent learning problem to see is there anything that we can do when we have more than one agent. So I think we have really the last not week before reading week, and we have introduced neural network and how to learn over the neural network. Have a quite quick overview of this deep learning field and some of these relevant techniques. And we haven't really touched the reinforcement learning. So this Monte Carlo traces topic we haven't really touched just yet. So I think actually it's good that I was talking about it later after we finish off this Q learning. Perhaps this is better arranged. Then we directly go to Monte Carlo traces and then reinforcement learning. So bear with me, and we will go back to the this Monte Carlo research in a minute. Okay, so today, in fact, we have quite a lot of slides. As you can see, 140 slides. So I would try to give a very detailed introduction about value-based approaches, and also give some of this theory behind it, and the development will be quite I will try to talk about this topic in detail, but in terms of proof, only touch this Q learning, and later maybe the week after, and when we will go back again to this single agent response learning and to continue on, for example, policy-based, and after policy-based, and we will give a more mathematically rigorous treatment on the subject. And we're talking about, what happens if you have a neural network approximation for the policy or for the Q value function, and what would be the case that you don't really know the model and you need to sample the data, what kind of sample complexity would look like. So hopefully with total 6 hours, and you would have a reasonably good understanding of reinforcement learning, which otherwise need an entire module to talk about. But I hope to cover the this principle behind it. In terms of various of method, because there are tons of algorithms, right? So the core can be classified into either model-based, model-free. In model-free, could it be the value-based and policy-based? So I think I would hope that after the 6 hours in total lecture, you would definitely able to comfortably reading all these papers, even though some of these specific techniques we don't really cover, but I have confidence that you would able to read the papers with no problem. I think that's the goal of it. And with that, then you can extend those things to the multi-agent cases and make use of some techniques, even for the task that in the coursework, and also for the any future tasks that you might encounter. Okay, so just to recap, and for the first 4 lectures we got in this module, we have been, focused on game's theoretical view on this multi-agent systems. And in particular, we have a bit of taste on learning in the sense of solving to find Nash equilibria. But we haven't really talked about, a form of a kind of proper learning. When I say proper learning, is that you got a bunch of data. When you got the data and you try to improve your algorithm by making use of data. And then in the 5th lecture, right before the reading week, and I think you learned these neural network, a deep learning or general, what is, machine learning in general, and you got this, concept of learning through, neural network. And now we're using this as a weapon or with tools, and to see if actually we can solve a decision-making problem for the remaining, 5 lectures. So the learning in single agent is that, think about it, is the agent now has become a single unit now. And what we want is that the agent might have certain goal. And they, based on that, they try to maximize that certain goal. And that will be equivalent to, in some cases, it will be equivalent to this rule mean square error that we're talking about in machine learning, is that they also have a task, try to make a prediction. In most of the things that try to make a prediction, you want a prediction as accurate as possible. Therefore, the goal is to minimize certain things. For example, rule mean square error. Or this in the collaborative filtering, they try to predict that the items that user are interested in, like books and movies that user are interested in, and try to predict the user clicks. So they all can be considered as making decision, and the goal of that is try to learn a function, right? As I said before, you have a neural network to represent that function, become parameterize representation of that function. The function input is some of the state, some of the features. The output would be your prediction or your decision. The goal of that is try to maximize certain reward or certain goal. So the same thing for the reinforced learning. So the only difference that they try to learn taking actions, not rather than try to making predictions. So this is a typical case that let's taking a game, the computer game as example, Atari game in this case, that suppose you have an intelligent agent and they observe what's happening in this game, let's say the observation OT. And then based on that, they take an action. This action could be some control of a certain, like let's say, game console, and then to control some of the, let's say, in this case, I don't know, is that flight? Control the flight, and then to see what's the system or the game do. The system would, based on that action, they would transit to another state, meaning the other image, and also give you reward. This reward could be, whether any score you got, whether if you died in this game, then the finish game you basically have a 0 score, basically you lose. Give that kind of a mechanism in terms of reward you or punish you in terms of the scoring. And then the system would continue based on this observation and reward and try to figure out what is the optimal action given current context image, so that I can able to survive in the game. Just wanna check, and do I need to? No, okay, yeah. So that create a kind of feedback loop between observation, action and the reward. Reward can consider as kind of feedback, and action could be as the kind of signal sent back to the environment. So with this kind of abstract model for taking actions, and then people can make use of do a lot of things. For example, as I said, that AlphaGo able to compete with the human in terms of certain games. So today I'm going to talk about is that going to focus on what is reinforcement learning, what is the underlying the process, which is a Markov decision process, and we're talking about the simple way of doing it. Assume you know the environment model by using dynamic programming, and then we go to the cases that suppose you don't really know the environment model. In other words, that the mechanism of the how environment change over time. So if you do not know that information, what you can do about it. And then we're talking about various of basic algorithms, and give you some of the simple proof in terms of convergency, but in the tabular cases. And then we'll go to this AlphaGo kind of setting, is to looking at Monte Carlo choices, a specific game that you know the system dynamics, because you have very simple system dynamics. But in that case, you have quite large decision space, what you can do about it. So reinforcement learning, as I said, is the problem of how to learn to take action. The goal is try to maximize certain objective, in this case long-term objective. And so the interesting thing about it is that in fact it's quite consistent with what human taking action. Obviously there's some sort of assumption and limitation, but in general they cover this so-called perception, sensation, to feel, sense the state of the environment, the outside world, and then based on that taking actions. And the goal is try to maximize certain cumulative reward. Right, as I said, given time set, receive observation from environment, taking action, and receive reward, and also environment based on action change to the next stage. Therefore, emit the the new state signal back to the agent. The agent based on that, and also based on the reward signal to taking action next, and so on and so forth. So, and then because of that, then you would, as an agent, you will collect the history. The history is really a sequence of the actions that you received, include the actions, include the rewards, and also include the observation about state. So you got this history, like the old observation at time step t, these rewards and the action, and observation, reward, action, so on and so forth. Then the idea for you is that you get, based on this history, you from that, and you want to come in with your option, your action, and the system is basically a function of history, right? As in the history, the state is that you need to have a certain measurement of what's happening on the environment, and because of that, you could have some information that about the environment, right? And then you can define this sort of the state of the environment, and some of the states might be observable, some of the states may not. So depending on that, you might have what I call the Markov decision process, or a POM-DP is partially observed Markov decision process. But today we're going to really focus on this Markov decision process. So the policy, some of the terminology. So policy is this learning agent's way of behave at a given time. So in other words, it's a function mapping from the state that observed to the action. So you could have this, given the state, you're taking action from that. So remember, in the game theory, we're talking about the policy. It's actually the same thing, right? The policy could be your strategy that decides in what situation, what kind of action you're going to take in. So again, here could be two cases. It could be deterministic policy, or it could be a stochastic. You could have in the game theory terminology, we talk about a mixed strategy, right? You could have a random sample over your action, But here is that we would have dependent something, right? When we talk about normal phone game, we don't really depend on anything. But if you have a sequential decision, then you can allow you to depend on something. Remember, we have studied a repeated game, right? We depending on this opponent's behavior, we're taking actions. So in that case, the policy is a mapping from the state that include the opponent's action. And based on that, you figure out your current action. And reward is that at each time step, you will receive the reward. That is way to define the goal of the higher program. For example, if you play chess, that you probably not receive reward in every time steps, but you do receive the reward at the end of the game, whether you win that or not. The value function is a way to represent that given current state of the game, right? Given the current state of the game. For example, it could be in the Atari game, this the image of current the situation happening in the video game, and then it's the value itself indicates if I starting play the game from current state, right? What would be the accumulated reward I'm gonna receive until the end of the game? Okay, so they basically evaluate how good, how bad this current state would be, right? In the chess case, would I be current situation? What would be the chance that I'm gonna win, right? So you can use that kind of chance from your, assessment of the, the value of current state. So in other words, properly the definition is like the value function is a prediction of accumulated future reward. So in other words, that you could consider it as is an approximation or estimation of the accumulated future reward. Yes, so this value function is play an important role because that tells us that how good are we at the current situation. That would help us to guide us to figure out the best move starting from now. So that will be clear mathematically later. And the model, okay, the model environment. When we talking about reinforcement learning, you probably heard people say it's a model-based solution, it's a model-free solution. So when we say model, it's actually have a specific meaning here. The specific meaning here is that the model of the environment. So when we say model of IR, it typically means that, not necessarily the model of the policy or model of the anything else, but rather the model of the environment. Okay, so what do we mean the model of environment? The model of the environment is that we have quite abstract representation of the environment, of the world that the agent is interact with. Is that given this current state, right? For example, this where I am in the Go game, okay? And this agent taking action, what kind of action this agent taking? And give condition on this, this system would transition to the next state. For example, if I in current state, I have my action is go to, mate, okay, check or mate or checkmate in the chess case, then the system would transition to that case that maybe next stage I'm gonna win, right? In that situation, I did have a checkmate situation, therefore that leading to the winning of the game. Or in the Atari case, that if I control this, little robot, either flight or anything that to attack these enemies, and then I would be able to kill one of them, okay? And then the next transition is that one of them vanished in the image. So you got this sort of a environment model. You can consider that is a game engine, right? The game engine basically is trying to design that. All the certain rule of the chess is actually need to, those rules actually define that transition. So the transition could be deterministic or could be stochastic. So let's just looking at this example here. We're starting a maze from the left side, and then the state is basically the current location of the agent, and the action could be, I will go to north, I will go to east, or I will go to west, or so on and so forth. And the state transition is really that when I given the current state, if I taking north, then the system transition would mean say I would transition to this state, from this state to that state if I take action here. But of course, in this case, that you don't have that action because it's you hit the wall, and if you have taken that, you'll go back to your current current state. You depend on how you define that. It could be said that if you go to that, there's hit the wall, you go back to the original state, or you say that action is invalid. So if you have that definition, you have this the game dynamics, the transition of the game, and then you can define say our starting point here, and say this could be state 0. And the goal of that is that I would allow this agent after number of steps, hopefully can reach to here, get out of this maze. And we could actually design the reward is that we say each time you make a move, either here or here, and there's effort, therefore you have received a negative reward -1, right? Then you basically if a certain policy, you actually able to evaluate how many steps that basically count how many steps that allow me to reach to the goal, right? You basically try to minimize that the steps that you're gonna have in order to achieve that goal, right? So this so this remember here the reward is given this sort of -1, so basically you can maximize that essentially is minimize your steps. So then the policy here is basically is given what state, like given is this state, they basically go to right side, or given this state go to this north. So the arrow present the policy pi s, right? Here you don't have this sort of a functional representation, let's say, but we can visualize it to say that in what situation, in what state, what kind of action you are taking. So the value function is that given the policy previously, right? And then you can actually calculate how many steps or how many how many steps that you need to take in order to reach the goal. But in this case, for example, you have just one step. If you're just looking at this policy here, then you have one step, then reach the goal, right? So here is that I've written down specifically this value function is dependent on the policy. It's policy dependent value function. That given that policy, that I only need -1, I only need one step to reach the goal. Therefore, my sort of value function is reasonably higher than my value function here. If I were in this state, it would take me 14 steps to reach the goal.